Bonjour, Raphaël.
Bonjour, Denise.
OK. Donc, la prochaine présentation sera en anglais. Notre ami Raphaël parle plusieurs langues, mais se sent beaucoup plus à l'aise pour présenter en anglais et je respecte et ça permettra à notre traducteur de changer l'élément de traduction. Donc, Raphaël Ponce travaille pour la compagnie Esri au bureau chef à Redlands en Californie. Elle est Maritime Consultant at Esri. Raphaël j'ai pas avec moi une biographie détaillée, pourra se présenter avec un peu plus d'informations. But he is a former national hydrographer from Mexico. He has been with Esri for more than 10 years, so I'll let him introduce further his bio. He will present to us this today on hydrospatial infrastructure on the fly. As I mentioned in my opening address, Raphael is a committed member of the hydrospatial movement, club, and community, and we are working together to promote further hydrospatial, and I'm happy to see the title of this presentation. So without further ado, the air is yours, Raphael.
Thank you, Denny. And let me see if I can you see my first slide?
Yes.
Perfect. And you see the presentation mode, not the presenter's mode, right?
Yes, we see the presentation. Yeah.
Okay. Well, thank you, Denis, for the introduction, and bonjour à tous. Merci de m'avoir invité aujourd'hui à cet événement important et intéressant. Cela aurait été un plaisir pour moi de pouvoir faire cette intervention totalement en français. Malheureusement, je ne connais pas la terminologie en français et comme vous pouvez voir, ma prononciation n'est pas la meilleure. Du coup, je vais devoir faire la présentation en anglais. Je vous remercie de votre compréhension. Désolé. And with that, I will continue in English. So I would like to start by giving a brief description of why we are calling it hydrospatial. Denis already presented a very interesting way and approach of how we are managing this word, but I would like to start with this in the context of a hydrospatial data infrastructure. So hydrography traditionally has been understood as a seabed measurement, usually represented as soundings or depths in a nautical chart. That basic concept has changed. Today, hydrography uses different methods to collect and analyze geospatial data in the aquatic environment. Not only the seabed morphology and the depth measurements, but also water column data together with tides, currents, water temperatures, and other parameters that support hydrographic survey. This geospatial data that is coming from workflow of collection, analysis, and production in the aquatic environment is what we consider hydrospatial. And the new IHOS 100 standards, I think, will be more relevant through a hydrospatial data infrastructure. And just the graphic that you see on the right side is Spillhouse projection, and it projects the entire ocean of the world together as it is connected. So we can see that there is only one ocean. We have different regions, but it's only one ocean, and I added the rivers. And for me, this is kind of a way of representing the hydrospatial world as a whole. So I wanted to use this catchy phrase of on the fly in reference to existing cloud services readily available to stand up HDI or hydrographic data infrastructure based services. So we have concepts like in cloud computing, like infrastructure as a service, platform as a service, and software as a service. Big data, not only in terms of the quantity of data, but also the velocity at which you can access that data and the availability of it. Of course, the Internet of Things that can be considered the interconnection via the Internet of different computing devices embedded in everyday objects, enabling them to send and receive data, and artificial intelligence and deep learning to perform analysis using all of the above technologies. And we will see an example of software as a service and the Internet of Things in a moment. So there are many patterns of cloud usage by the hydrospatial community in which ArcGIS has been deployed in the past. I mentioned infrastructure as a service, and with that, you run traditional software, but the hardware infrastructure, the physical servers and networking equipment on your premises is replaced by virtual machines and virtual networking provisioned and configured using the administrative interfaces of the cloud platform on your of your choice. With software as a service, everything is hosted and managed by the software vendor. Once you're running in the cloud, there are additional cloud native features provided by the cloud platform. The common features include storage and database options that are specific to running in the cloud. This kind of functionality now is referred to as platform as a service and provides building blocks to run highly scalable and highly resilient software deployments. In Esri, the new ArcGIS platform provides access to comprehensive, high-quality set of location services to build useful capabilities into apps and solutions and deliver geospatial content. One can embed mapping and analytic capabilities in one's apps, like, for example, data visualization, geocoding, and searching, directions and routing, and spatial analytics. One can supplement one's data with ready-to-use base maps and data services like demographics, points of interests, live feeds, imagery, and more. So traditional deployments are like this first graphic on the left side. Originally, organizations ran large applications on physical servers in their organization. In this deployment, the resources boundaries were often poorly defined. So if multiple applications were run, one application might use up most of the hardware resources, for example. Scaling was very difficult, mainly due to inefficient use of resources. Then we have the virtualized deployment. With virtualization, you can run multiple virtual machines or VMs on a single physical server, CPU. These applications can be isolated between VMs, between these virtual machines, and this isolation provides security between applications. Virtualization allows better use of the physical resources and provides better scalability than the traditional deployments and reduces the organization hardware costs. Essentially, each virtual machine is a full machine consisting of an operating system and a virtual hardware. And the last one that I want to show here is the container deployment. In this container deployments, it's a step beyond virtualization. Here, the operating system can be shared by the application itself. In some aspects, containers have similarities to the virtual machines. with the exception that the components of a containerized operating system is portable or created and destroyed across the cloud or multiple clouds. This can be done with ArcGIS Enterprise and Kubernetes, and can be deployed on Windows and Linux environments. So I mentioned Kubernetes. What is this? And not everybody is familiar with this new type of approach. So Kubernetes is an open source orchestrator for managing and deploying containerized applications at scale that was originally created by Google. Software can now be delivered as microservices, in which an application is a collection of loosely coupled services. The approach to using microservices is new and used to easily scale and develop on. To do this, microservices need to be orchestrated centrally in order to better use resources and deploy applications quickly. Kubernetes are also used to manage the life cycle of the containers where they are located, allowing easy creation and destruction of them as well, as I mentioned before. And if you want to learn more about Kubernetes, you have the link on the lower right of the slide. So I want to give an example, and I want to use something called ArcGIS Velocity, which is a cloud-native add-on capability in ArcGIS Online, the software as a service of Esri that enables users to ingest data from the Internet of Things platforms, also from message brokers and third-party APIs. It also helps users process, visualize, and analyze real-time data feeds, store those feeds as big data, and perform fast queries and analysis. And you can use this software as a service IoT application to better leverage any real-time spatial data for essential operation decisions, such as, for example, remote monitoring of assets, predictive maintenance, and process optimization. Something important to highlight is that all the analysis is performed in the cloud. There is no software installed on the local machine. So now let's look at how ArcGIS Velocity could support or can support the creation of real-time ship's position analysis and the combination with other sources. So first, I have created a data feed using ArcGIS Velocity with a configuration wizard. From here, you can select the type of feed that you want to use, and you can see here on the screen capture on the right that we can do it from an ArcGIS layer, from which we can create a feature layer as an output or a stream layer or both. We also have the possibility to make feeds from the cloud, from an Azure or an Amazon or a Cisco cloud, for example, or from web and messaging applications like HTTP or Kafka or RSS. Then I use the BOEM Marine Cadastre AIS data. So BOEM is the Bureau of Ocean Energy Management in the United States. And this organization, together with the National Oceanic and Atmospheric Administration, or NOAA, have worked jointly to repurpose and make available some of the most important records from the U.S. Coast Guard's national network of automatic identification system receivers. So I took that, and then I used the configuration wizard to define how to construct geometry, date and time, and the tracking information. But since the data source is a feature layer already, the geometry, date and time information is automatically configured. And by the way, I want to mention here the new US vessel tracking app in the Esri Living Atlas. And you can see here in the lower left the link to that. I think it's a tool that lets you explore the paths of vessels in and around the United States waters. You can look for patterns and trends by time, by vessel type and place, and it provides a simple and efficient way to download manageable sized area-specific excerpts. So if you have time, you can check it out later. So once the link with the AIS service has been established, the feeds are started. So there's a button here that says run. So I have clicked this button and it's running. And the blue dots that you see on the here in the upper right are the ship's AIS feeds that I connected to the service. Then the service can be opened in using an ArcGIS Online Map interface. So you can see all the blue dots in this interface here. And you can query the AIS data that comes from the service. And here, the AIS data can be combined with other services, such as, for example, an ENC service. In this case, I'm taking the NOAA ENC service. A possibility could be here to analyze maritime traffic in traffic separation schemes, in marine protected areas, risks zones, shallow areas, etc. So now, after creating the feed, we are going to add data to perform some analysis with this AIS feed and publish that as a feature layer. So publishing a feature layer allows you to publish a separate feature layer which contains just the latest observations, which is useful if you want to symbolize the current position of an asset. In this case, we have ships, and they are differently symbolized in the web map, so you can tell which ones are the ships. I used the Boeing Marine Cadastre for that and designed a real-time analytic. That's what I will show in a moment. And I will configure a stream layer output too. And then you can also look at real-time metrics and analytics, how many people is looking at it, how many computations are happening per minute, etc. So the way in which this type of analysis is done is by combining the services similarly to the way ArcGIS Model Builder works. You're familiar with ArcGIS. So here I'm using the AIS data from the feed and then selected a US Coast Guard districts layer to perform the geospatial, or in this case, hydrospatial analysis, combining the two feeds by joint features. So I have the two feeds here on the left. You see the ships coming from the AIS and the US Coast Guard districts as a feature layer, combined with this tool, that's joint features. And I will create these two outputs. So we have the option to publish feature layer, which keeps the latest observation for each track ID, and the option to select a related feature layer to provide geometry when the stream layer is drawn in a map.
So Rafael?
Yes?
You have 3 minutes.
All right, thank you very much for the warning. So here is the screenshot of the US Coast Guard districts with the blue dots of the ships in it. And now if you see, when I click the ship here, as part of the information for each ship is the Coast Guard district. So something that didn't come with the AIS. And now I merged this information together with it. And there are many possibilities using big data for doing statistical analysis to reveal trends, heat maps, risk analysis. And this was just a quick example of how geospatial analysis can be performed on the cloud. So a recap of this example, I created a data feed using the configuration wizard and the BOEM Marine Cadastre AIS data. Created a real-time analytic combining the U.S. Coast Guard districts for each ship, where they are with respect to these Coast Guard districts, all in real time, all in the cloud, using software as a service. Now, how can we understand hydrospatial as a marine spatial data infrastructure? Well, an HDI is all about sharing data, right, and services to stakeholders. Many people in the past have thought of an SDI as a type of data warehouse, but HDIs, or hydrospatial data infrastructures, are much more. And things like web services, mapping services, and apps can be shared as well. And I show here in this little graphic how an HDI can expand to a national SDI, a regional SDI, or even to a worldwide SDI, because they can all be interconnected. Some of the benefits of hydrospatial is easy to deploy on the cloud. Cloud native is easier and utilizes more efficient use of container images, or the Kubernetes that I mentioned a moment ago. It provides reliable image builds, deployments, and quick rollbacks. You can have health metrics where you can observe not only the health of the operating system, but also the applications as well. It's portable. It runs on Ubuntu, RHEL, Core OS, on-premise, and on major public clouds, and it's loosely coupled. Microservices are broken into smaller independent pieces and can be deployed and managed dynamically. So there is no need for a huge program on a single machine. And I think with that, I've finished my presentation. Merci beaucoup. Thank you very much.
Merci, Raphaël.